Hello, welcome back to another video. Today I'll be going over mutual inductance. I'll be going over this problem, 13.11, and then I'll be going over 13.14. Alright, so before we get started, I'm just going to talk about the circuit right here. So right now, our components, like our inductors and our capacitors, are not in the correct form we want them to be in. So we want to convert all these so they can be in ohms, so they can have their impedance. And same with the voltage source and the current source, is that they are in just their peak form, and we want them to be like in the form we can use. All right, so, and also in the circuit we have two inductors that are going off of each other. So we're going to need to, everyone's going to hate this, but we're going to need to introduce a dependent source into here. But before that we do that, I want to first assign a current flowing through this component right here of this inductor. Because with that, we'll be able to tell which way or what type of dot convention we want. What I want to do, I want to have positive dot convention for this. You can do negative dot convention, it doesn't really matter, just make sure you're consistent with what you do. So I'm going to say that the current is going to be coming this way. So we have IL coming that way. So now it's time to convert all these components into their impedance form. Okay, so first I'm going to start off with the sources. This is the easiest to do. Oops, drop that, whatever. First, I want to do the voltage source over here. So it's 110 cosine 600t plus 30 degrees. So the magnitude is simply just going to be the same, so it's 110. And then the phase angle is just going to be 30 degrees. And now I'm going to do the current source, and that's magnitude is 4, phase angle 0. And thing to remember is that omega is equal to 600. 600, not 606. Okay. So now, with those two sources, I'm going to move on to the inductor, capacitor, and this inductor over here, and the mutual impedance. So for inductors, remember, is J omega L. So J times omega, which is 600, times 1200 is going to be equal to 720J. Oh, I have two J's there. And then use the same equation for the 800 millihenries. So it's going to be, this is 480J. And the mutual impedance is still the same formula, J omega L. So 600 microhenries times 600 times L, or times J, is equal to 360 J. All right, now finally the capacitor, which is going to be 1 over CWL, or the capacitance times omega times J, not L, J. So this is going to be equal to negative 138.9 J. And all these are in ohms. I'm a little cramped for space over here, so I don't want to write them all out. So now we get to the fun dependent sources. These guys, since I have positive dot convention, meaning that the current flows out of both of them, that means we're going to assign our voltage drop or rise as a voltage drop with respect to the current. So we're going to have plus, minus, and then the current's coming this way, plus, minus. And now simply the value of this voltage source is simply going to be the mutual impedance times the other current. So it's going to be, for this one down here on the IX current, it's going to be 360 times I0. Oh, don't forget the J. And same thing with this one over here. It's going to be the mutual impedance, which is 360 j times ix. Okay. So now that we have all that started, we can start doing KVL around these loops. Actually, one more thing before we get started. I see this over here, and I don't like that, because these are in parallel with each other. I see that and I recognize that I could do source transformation right there to get simply a voltage source in series with a resistor. So let me do this. The resistor stays resistor value stays the same, so it's 200 ohms. But this is no longer a current source; it's a voltage source. So using Ohm's law, it was 4 amps times 200 is equal to 800. Phase equals 0 volts. All right, so now we're ready for KVL around these loops. So to assign KVL, I'm going to first, or do mesh analysis, I need to first assign currents. So since we already have IO going this way, I'm going to assign IO in this loop. And then I'm going to assign another current I1 right there. It's just an arbitrary current just for us to find IX later. Speaking of IX, now that we have these two currents, we can define IX. IX is going to be equal to I1 goes down, so is IX, so that means I1 is the positive part. And since IO is going to go against IX, it's going to be minus IO. Perfect. And now we are finally ready for the KVL loops. So first I'm going to start off with KVL around IO. Okay. So there's quite a few terms in here, but we can break them down pretty easily. So I'm going to start over here at this voltage source. So our current is going to flow through the positive, so we're going to have 800. And we'll come down around, and it's going to be minus 360 I0, J. And then we're going to flow through this 720 J ohm inductor. So it's going to be plus 720 J. But since this component shares both currents, I'm going to do IO minus I1. And then we're going to come through this dependent source through the positive terminal. So this is going to be plus 360 J times IX. But we don't want to solve for IX right now. We just want to solve for I1 and I2. So I'm going to substitute IX for this equation we just found. So it's going to be I1 minus IO. And then we're going to go through this 480 J ohm inductor. So this is going to be plus 480 J times IO. And then finally, we're going through this 200 ohm resistor. It's just simply 200 IO. It's all equal to 0. Pretty long equation, but it gets simplified pretty simply. Okay. So I'm just going to go to the simplified form. You guys deal with all the fun algebra. It's going to be simply equal to IO is going to be equal to 200 plus 480 J minus 360 J I1 is all equal to negative 800. Phase equals 0 degrees. Boom. So now that we have this equation, we also want to work on our second mesh equation, which is going to be I1. All right, so let me move my chair right here. Okay, I1, KVL I1. Okay, so I'm going to start at the voltage source once again. So we're going to come through the negative terminal, so it's going to be negative 100, phase angle 30, and then it's going to be plus 150, I1, right, yeah. I1 minus 138.9J I1 plus 720J. And since we are doing the I1 loop, we want the I1 to be positive over here. So we're going to have I1 minus IO, and they're coming through the positive terminal of this dependent source. So that means it's going to be plus 360J times IX, but we already have IX defined as I1 minus IO, and that is all equal to 0. All right, so now that you guys can do the fun algebra of reducing that into just IO and I1, it is going to be equal to 300 and negative 360J times or plus I1 times 150 plus 581.1J is all equal to negative 110 with the phase angle of 30. Boom. And now that you have equation 1 and equation 2, you simply just put that in your calculator and solve. So what you get is that I0 is going to be equal to 2.031 129.6 degrees, and then I1 is going to be equal to 1.038 with the phase angle of 145.8 degrees. And these are all in amps. So now that we have our two currents, we can simply plug that into our IX equation to find IX. So it's going to be 1.038 with the phase angle 145 minus 2.031 the phase angle of 129.6. So that will get you equal to 1.07 with a phase angle of negative 66.04. And I'm pretty sure that's the right answer. I think in the slides, the answer is 1.1 with the phase angle of negative 65. I think that's close, 65.8. I think that's close enough. It's just rounding errors because I probably kept in the longer decimals like these in the thing. So I'm pretty sure that's the right way to get it. Yeah. Here's our next problem. This problem is going to find Thevenin's equivalent. So it's going to be a lot of fun because we have to introduce dependent sources, which means we have to do that stupid little extra work for finding ZTH. But everything will be fine. Don't worry about it. Don't stress about it. But looking at our circuit right here, I look over here and I instantly see a nice spot to source transform. Another thing is that the inductors, they share the same current because they're in series. So what that means is no matter how we assign the current, we're going to have negative dot convention. All right, so I have introduced our two dependent sources we're going to need, one for each inductor. And I've also source transformed to this right side. So now we have a 40 volt source, and then the 2 ohm resistor is now in series with everything. Okay, so now what we want to do is do our dependent sources. I can't think of the words now. But I'm going to say that the current is going to be IO, and it's going to be flowing this way. IO. Okay, so that means since we have negative dot convention because the current is entering and leaving each inductor, or enters right here and leaves over there. So that means we have negative dot convention. So that means that our dependent sources are also have to be defined with a voltage rise. So that means we're going to have plus minus and plus minus. And what is the value of these? It's simply just going to be the value of the mutual impedance times the current of each inductor. So this is simply going to be 2J. But since the thing with this problem is that they share the same current, they are defined as the same voltage rises. So they're both 2JIO. But if you're like me and you want to try to make the circuit as simple as possible, you can't really do that in this case. I mean, you can do like this side right here, you can combine these components, but what you want to do is make sure you keep these two nodes the same. So we can't combine these two and make it 4JIO, because then we would be getting rid of this node, and at the end, I mean, you can do that, but at the end you have to unravel it, and at that point you're just giving yourself more work and more places to make mistakes. So I'm just going to keep our circuit looking like this, which is ugly in my eyes. But anyways, first we need to do is find VTH. So VTH is simply going to be the voltage from A to B. But before we get there, how I solve this is that we have to find the voltage across every one of these components. And to do that, we first need to find IO. So over here, I will do finding IO. And IO is just a simple 1 KVL loop. So that is going to be equal to 5IO, because we're going this way through this resistor, then through this inductor, through this dependent source, inductor, capacitor, resistor, and then through the voltage sources. All right, so it's going to be 5IO plus J6IO minus 2JIO minus 2JIO plus J8IO minus 3JIO plus 2IO plus 40 minus 50J equals 0. All right, now do the same algebra later. You'll find that IO equals 7 plus 7J, and this is all equal to negative 40 plus 50J. And now you can just use a calculator to find that IO is equal to 6.468 with a phase angle of 83.66 degrees. Sweet. Now that we have IO, we can now solve for VTH. So what I'm going to do is that I'm just going to do this right side, but because there's less components, but it's a little trick that you can, I'll show you guys. So you're going from positive to negative terminal. So I'm going to start right here. I'm going to come up through here, through this dependent source, through the inductor, through the resistor, through this voltage source, and then we're finally back at B. But since our current is defined as going this way, all of our source, all of the resistor and the inductor, we're going to be having rises the entire time. So that's a little mishap that can happen. All right, so VTH is going to be equal to, it's supposed to be 2JIO minus J6IO minus 5IO, and that is plus 50J. And all you have to do is punch in IO and substitute in for all these values, punch that into your calculator, and you'll get that VTH is equal to 26.75 the phase angle of 34.11 degrees. Boom. We're halfway done, probably the easier part of the problem. And yeah, all right, moving on to ZTH. All right, so the fun part of this problem is finding ZTH. So ZTH, it would be nice and simple if we were like 2 weeks ago when we didn't have these dependent sources in our problems. But since we do have our dependent sources in the problem, we are going to have to introduce a voltage or current source into this problem in order to find VTH. So what I like to do is to put in a voltage source. You can put in a current source. Actually, in the slides, they do a current source, and it makes it a little bit easier, but you just have to remember your rules for super meshes. So what I introduce is a 1 volt source. All right. So now with that done, we need to find our current. So now we're trying to find this I/O current that's flowing through this 1 volt source. All right. But what we need to do is define these two currents on each side. So I am simply just going to say that this is I2 and this is I1. So with that said, we now have new currents, and therefore we need to redefine our dependent sources. So it can be said that our sources now are going to be nothing changed, but because we're still in negative dot convention. But let's say I made I1 going this way, then they would both be leaving, and that would mean we have positive sign convention, but positive dot convention. But since we still have negative, it's still the same thing as negative plus, 2J, 2J. But it's not I/O anymore because each inductor has a different current now. So this dependent source is going off of this inductor, which is current is going to be I2. So instead of 2J I/O, is now 2J I2. And with this dependent source, it's going to be with reference to this inductor, which has a current of I1. So this is now 2J I1. So I think that is all we need to do to define our circuit. Yes. So now with all this said and done, we are now prepared to start solving for this I/O, which allows us to solve for ZTH. All right, so now let's do this mesh analysis so we can find I/O and ZTH. All right, so I'm going to start with KVL of I1. So the KVL of I1 is pretty simple. It's just going to be 5, this 6J inductor, this source, and then this source. All right, so it's going to be 5 I1 plus 5 plus 6J I1, 6J I1 minus 2J I2 plus 1 equals 0. All right. So now if you just move some stuff around, it's I1 times 5 plus J6 minus 2J I2 is equal to -1. And now we're going to do KVL around the I2 loop. So KVL of I2 is going to be pretty much the same exact thing, but with some different, just one different component pretty much. So now we still have the source, this dependent source, inductor, capacitor, and resistor. So it's going to be, I'm going to start at the source, so it's going to be -1 minus 2J I1 plus 3J8 I2 minus 3J I2 plus 2, no longer J, just 2 I2 equals 0. So moving stuff around, you get that it's negative 2J I1, so I to the I, Ji1 plus I2 times 2 plus 5J equals 1. Now with that said and done, we are ready to plug in these two equations into our calculator. So after we do that, so we have equation 1 and equation 2. So you plug those into your calculator, and you'll get that I1 is equal to 0.159, a phase angle of negative 74.73 degrees. And we get that I2 is equal to 0.89, phase angle of 123. And the reason that I always use polar form is that I'm just too lazy to change the setting in my calculator, so I just keep it this way. All right, so now that we have I1 and I2, we can now find I0. So just like the last problem, I0 was connected by these two currents, but now we have I2 going with it, and I1 will be resisting it. So it's going to be I2 minus I1, and you just plug in those values for here, and you get that I0 is equal to 0.2453 with a phase angle of negative 68.39 degrees. Now that we have IO, we're now super close to finding ZTH, and ZTH could be no simpler than just using Ohm's law. So now ZTH is going to be equal to V0 over I0. V0 is just equal to 1, so it's going to be equal to 1 over 0.2453, negative 68.39. This will equal to 4.1, the phase angle of 68 degrees. There we go. And now that we have all this done, we have VTH and ZTH. We can simply say that this entire circuit can be whittled down to a voltage source, a load, here's A, here's B, and so this is ZTH, so this is 4.1, phase angle 68, and our VTH from earlier was 26.75 with a phase angle of 34.11 degrees volts. Boom. So now this ugly circuit is now just this. That's it for these problems. Good luck on the quiz.